Hello everyone, welcome to the first video lecture on the Safe in Cave simulator. My name is Tensorial and today I'm going to present some basic concepts related to tensors and tensor operations. This topic is very important for the future video lectures because not just solid mechanics but all the continuum mechanics heavily depends on a good understanding of those concepts. So this video has been divided in two parts. In part A, which is the one I'm going to present today, covers the theoretical part in a very simplified way, but at the same time I want to focus in the specific problems that we will face in the upcoming videos. In the second part, in part B, I'm going to use all that theory to solve some very interesting examples that hopefully it will make the theory much more clear. As a motivation, we want to know how to perform these operations here. For example, suppose C is a rank 4 tensor, epsilon is a rank 2 tensor, and we want to perform the double dot product. And what is the result from the double dot product between a rank 4 tensor and a rank 2 tensor, which would be this sigma here. So this sigma is also a tensor, but what rank, what order? Well, first of all, what is a rank 2 tensor? What is a rank 4 tensor? How many ranks can we have? What is a rank 1 tensor? And so on. So we want to have all these concepts very clear in our mind before proceeding, because this type of operation will appear a lot along this series of video lectures. Another example, which is a bit more applied, for example, to porous media, to deforming porous media, in which we have the stresses, the effective stresses, and we also have the pore pressure inside the pore spaces. Alpha would be the BO coefficient, but that's not important for now. I would be the identity tensor, identity rank 2 tensor. So I want to know how to perform the operation. This is the nabla operator, this is the dot product. Sigma is a rank 2 tensor, alpha and P are scalars. I is a rank 2 identity tensor. Well, what does this equation mean? How can we perform these operations? At a later step, how can we expand this equation in three equations, in the three coordinate directions? For example, here this equation can be split into this first one in the direction number 1, direction number 2, and direction number 3, and we have all these indices, sigma 1 1, sigma 2 1, sigma 3 1, and then we have partial derivatives with respect to x1, x2, x3. Now we have partial derivative of pressure with respect to x1 and yx1. Why do we have x1 here and instead of something else? We want to know how to perform these expansions here. Well, that's one way to motivate. I'm sure that these concepts are very clear for most of you watching this video. So if you are very familiar with this, feel free to skip these videos and proceed to the other video lectures. Otherwise, bear with me. That I'm sure you're not gonna regret this. Okay, so let's start the story from the very beginning. Suppose we have a vector here. A vector is a mathematical abstraction that is characterized by a length. Every vector has a length and it has a direction. It points to a direction, and usually we use an arrow to represent a vector because an arrow has a length and it also points to a direction. And the vector exists independently of everything. it doesn't depend on any coordinate system to exist. It simply exists. But in order for us to represent any type of vector, it is interesting, it is convenient for us to use to write this vector in terms of known vectors. So suppose we come up with three vectors e hat 1, e hat 2, e hat 3, all of them pointing to one direction, orthogonal to each other. And these vectors, this is what we call the basis vectors. And these vectors, they define different directions. They are all orthogonal to each other. Now, by defining these vectors, we can represent, by defining these three vectors, those red vectors, we can represent any vector living in this three-dimensional space based on those three vectors. So the only thing that we have to do is to take this vector v and project into the directions defined by those basis vectors, and then we can count how many times in each direction, for example, how many times we have from each basis vector. For example, if we project this vector v into the direction the direction defined by e hat 1, we can see that we simply multiply e hat 1 by 3, 1, 2, 3, then we have the first component of our vector. And then we project to e hat 2, and then we project to e hat 3. So this vector could be represented by this expression here. So vector v equals 3 times e hat 1, so 1, 2, 3, plus 2 times e hat 2, 1, 2, 1, 2, plus 4 times e hat 3, 1, 2, 3, 4. So this is a way to represent this vector. In a more general way, we can represent vector v, or a general vector v, as v1 in the direction e hat 1, plus v2 in the direction e hat 2, plus v3 in the direction e hat 3. This is just a way to represent a vector. Another way to represent the same vector is to use a column vector. So the first term would be the component of this vector in the first direction, e hat 1. The second term, the component in the second direction. And the third term, the component in the third direction. They all represent the same thing. It's just a way to represent the vector. They refer to the same vector. The vector v, as I told you before, it lives independently of anything. The only thing that changes is the way we represent this vector. We can rotate those basis vectors. For example, e hat 1, e hat 2, e hat 3, we can rotate those vectors, and then those numbers, these numbers 3, 2, and 4 would change, but the vector would be the same. The length of the vector would be the same, the direction of the vector would be also the same. The only thing that changes by changing the coordinate system or the basis vectors is the representation of the vector. Okay, so I'm pretty sure this is very, very basic. First year of engineering, everyone learns this. Another thing that is very basic is the internal product between two vectors. But I just want to present here to make it sure it is clear and we start from a common ground. So the internal product, also known as a dot product between two vectors. So suppose we have two vectors w and v. They point to different directions and they are coplanar, and the angle between those vectors is theta. Then the dot product between these two vectors is defined. This is a definition. The dot product between these two vectors is given by the length of vector v, or the modulus of vector v, times the modulus of vector w, times the cosine of the angle between these two vectors. This is by definition. One possible interpretation of this is that this represents the product between the length of vector v and the projection of w into the direction defined by v, and the projection of w into the direction of v is given by the modulus of w times cosine theta, or the other way around. We can think of it as the length of w multiplied by the projection of v into the direction defined by w, and the projection of v into the direction defined by w is given by the modulus of v times cosine theta. Okay, so this is just an interpretation, and this is the definition of internal product or dot product. Okay, now what are the implications of the dot product in our basis vectors? Remember, we defined three basis vectors, vectors that serve as a basis for us to write any vector that lives in the three-dimensional space. Another an important characteristic of those basis vectors is that they are all orthogonal to each other. So the angle between these vectors is 90 degrees. And the other very important characteristic is that the modulus of these vectors, the size of each of these vectors, is unitary. So the modulus of all these vectors is 1, equal to 1. So if we take any pair of basis vector, e hat I and e hat j, the dot product between these two vectors will be just the cosine between the angle of these two vectors, because the modulus of each vector, each basis vector, is always 1. So here we have 1 times 1. I don't need to write that. So the dot product between e hat I and e hat j would be just cosine of theta, which is theta ij, and theta ij is the angle between e hat I and e hat j. Okay, so if we analyze all the possibilities, we can see that the only situation in which the dot product is not 0 is when I equals j. If I is different than j, then the dot product would be 0. We can write that as this function here. So the dot product between e hat I and e hat j equals the Kronecker delta function. And the Kronecker delta function works like this. It returns 1 if I equals j, or it returns 0 if I is different than j, which is just what we said before. So this is very important. This result here is very important, and we are going to use this a lot in the video lecture of today, and in the next one, in the part B of this topic. So keep this equation in mind. Okay, another concept that I would like to introduce, that I'm sure that you know, but I would like to introduce here to show the notation I'm using, is the Nabla operator. And the Nabla operator is defined as a vector. The Nabla operator is a vector. I want to make something clear. I'm only considering a space with 3 dimensions. Mathematically, I can consider spaces with as many dimensions as I want, but I'm only considering 3 dimensions. That is why I'm only using e hat 1, e hat 2, and e hat 3. So the Nabla operator is the partial derivative of something with respect to x1 in the direction e hat 1 plus the partial derivative of something with respect to x2 in the direction it had 2, and the same thing in the direction it had 3. So this is the Nabla operator. This is an operator. This is not a number. This delta divided by delta x del divided by del x1 is not a number. This is a derivative that will be will actuate, will be applied to something, to a function or to anything. Okay, so this is an operator and it will return a vector. This is very important. Okay, now let's talk about tensors. What is a tensor? A tensor is a mathematical abstraction that can be used to represent physical quantities. It can be used to represent physical quantities, but it doesn't have to represent physical quantities. It can represent anything, but usually we use it, at least in the engineering realm, we use it to represent physical quantities, and we can have different types of tensors. We can have, for example, rank 0 tensor. A rank 0 tensor is just a number. The number of components that it has is 3 to the power 0, which equals to 1. So it has only one component. Why 0? 0 because we are considering rank 0. And why 3? Because remember that I told you before, we are only considering space with 3 dimensions. It could be any dimensions, any number of dimensions. It could be n dimensions. And if we have a space with n dimensions, then it would be n to the power 0, which would be still equal to 1. But in our case, n equals 3, and n being the number of dimensions. So every time we have a tensor of rank something, we will have 3 to the power rank. Okay, this is the number of components. So a rank 0 tensor has only one component, and this component is not associated to any direction. Okay, so this could be, for example, 42. 42 is a rank 0 tensor. In other words, usually we call rank 0 tensors, we call it a scalar. That's usually how we refer to rank 0 tensor. We're not going to say we're not going to call 42 as rank 0 tensor. We're going to say it's a scalar, right? But from the perspective of tensors, this would be a rank 0 tensor. For example, 42 could represent 42 megapascal, 42 degrees Celsius, 42 kilograms per cubic meter, and so on. And some examples of physical quantities that can be represented by a rank 0 tensor or a scalar would be pressure, temperature, density, volume, time. What else? Distance. Distance is also a rank 0 tensor. It doesn't make sense to ask, okay, the distance between 2 points is 42 meters. Doesn't make sense to ask to which direction. Well, what do you mean which direction? It's 42 meters. The distance between these 2 points, 42 meters. Doesn't have a direction associated to it. Same thing with volume. The volume is 42 cubic meters. To which direction? It doesn't make sense. So rank 0 tensor has only one component, and that component is not associated to any direction at all. Okay? Now, what about a rank 1 tensor? A rank 1 tensor can be represented by a vector. This is actually what we call a vector. Usually, when we say the word vector, no, not usually, but every time we say the word vector, we are referring to a rank 1 tensor. Rank 1 tensor has 3 to the power 1 components, which means 3 components. So that is a vector in the three-dimensional space. It has 3 components, 1 in each direction. And as we already we have seen before, this vector can be represented by a scalar, a component in the direction number 1, another component in direction number 2, and another component in direction number 3. So each component is associated to one direction, and it is very important. Each component in the rank 1 tensor is associated to run one direction only. We can also represent this vector by a column vector, like this, or like this, doesn't matter. And examples of rank 1 tensors are the velocity vector, heat flux, position. A position is also a vector because it is always measured with respect to a reference. The distance, on the other hand, does not depend on any reference. We can use any coordinate system. The distance will always be the same, but the position will not be the same. Okay. What about a rank 2 tensor? A rank 2 tensor has 3 to the power 2 components, which is 9 components. 3 because we are in the 3-dimensional space, and 2 because we are referring to the rank 2 tensor. We can think of it as a matrix. And we can represent this we can represent a rank 2 tensor like this. So for example, we have A11 in the direction E hat 1, E hat 1. Then we have another component in the direction E hat 1, E hat 2. And then we have another component in the direction E hat 1, E hat 3, and so on. So each component, so notice this, that each component in a rank 2 tensor is associated to 2 directions at the same time. It can also be represented as a matrix, a square matrix, in this case a 3x3 matrix. We can choose which representation we use. Examples of rank 2 tensor are the stress tensor, the strain tensor, the permeability tensor, and so on. Usually when we say tensor, it is very common to people to say tensor. When they say tensor, they refer to rank 2 tensor, because this is the first tensor order in which we actually have to call it a tensor, because for rank 1 tensor we can call it a vector, and that's what we do. We do not call a vector rank 1 tensor. We just say a vector. And the same thing for a rank 0 tensor. We just call it a scalar. We don't say rank 0 tensor. But for a rank 2 tensor, we need to call it a tensor. So sometimes when we say, suppose this is a tensor, usually it means a second order tensor or a rank 2 tensor. By the way, we can say a rank 2 tensor or a second order tensor. We can say a first order tensor, or we can say a 0 order tensor. For example, we can say third order tensor or rank 3 tensor, and so on. A rank 3 tensor, as you might suspect, has 3 to the power 3, which is 27 components. We can think of it as a series of matrices, one behind the other, and a possible representation is like this. So each component is associated to 3 directions. For example, this one is associated to direction E hat 1, E hat 1, E hat 3, E hat 2. Each component associated to 3 directions. We can think of it as a series of matrices, and one example of physical quantity that can be represented by a rank 3 tensor is the piezoelectric tensor. To be honest, I didn't know any physical quantity that could be represented by a rank 3 tensor. I googled it and I found that piezoelectric tensor is a rank 3 tensor, and I can't find any other example of this, of a physical quantity that can be represented. Actually, I've never seen a rank 3 tensor when I was working. Now, a rank 4 tensor has 3 to the power 4, which is 81 components, and the representation is like this. Each component is associated with 4 directions. Now it becomes more difficult to use the representation of a matrix. You see, what we cannot, up to the rank 3, we always had, because we live in a 3-dimensional space, up to the rank 3, we always had an extra dimensions that we could use to represent the new components that appeared. So for example, here we have rank 0, then in rank 1 we have one direction here in which we can put some cubes. Then rank 2 we have another available direction. For rank 3 we have another available direction. For rank 4 we ran out of directions, so we can think of it as a series of blocks. Okay, and more or less like this. It's a bit complicated because it will be actually rank 3 is a cube, rank 4 would be a hypercube, but we cannot represent a hypercube in a 3-dimensional space. We can only project the hypercube. But you get the idea. It's difficult to represent, but we can have as many ranks as we want. We just can't represent them in a nice way anymore. But in any case, they can always be represented like this. So each component is associated to 4 directions. And one example of this that we're going to see a lot is the stiffness tensor. Another example that I didn't know, I had to Google it, is the Riemann curvature tensor, which has to do with physics, theoretical physics. I don't know what that means, and I'm not sure if I'm sure there are more physical quantities that can be represented by rank 4 tensor, but I'm not aware of. So this is a basic overview of what tensors are. They can have different orders, and they are just mathematical abstractions, or we can think of it as data structures. They are data structures that can represent different physical quantities. For example, to represent stress, we cannot represent stress by only 3 components associated to 3 directions. It's not enough. The same thing, I cannot represent velocity with a single number. I cannot say that okay, the car is 100 kilometers per hour. This is not enough. We need to know which direction, because if it's in our direction, we would better get out of the way, right? So it's important. It's important to know the direction for velocity, and the same thing for the other quantities. We need to associate quantities to different directions. Okay, I want to call your attention to the notation that we are using throughout these video lectures. So to represent a rank 0 tensor or a scalar, we're using plain Roman or Greek letters, just normal letters, regular letters. For example, P, T, V for volume, temperature, pressure. This is rho for density, for example, alpha for BO or hardening parameter. Anyway, they are all scalars. They are all rank 0 tensor. For rank 1 tensor or vectors, we use lowercase, bold Roman letters. So V, bold W, R, Q, all lowercase and bold letters. For rank 2, we use uppercase, bold Roman letters, for example, A, B, and Q. And we can also use lowercase, bold Greek letters, for example, sigma and epsilon for stress and strain tensor. Rank 4, I'm not even bothering with rank 3 because we're not going to use it. So rank 4, we use some fancy Roman letters. For example, this fancy A with double X, fancy B, fancy C, whatever that means. Okay, so this is the notation. Now, the other thing that I would like to introduce, and this is very important. This is Actually, I cannot stress enough how important this is, because it allows us to work with a lot of data with a very compact notation. This is the Einstein notation that most of you might have heard of. And the Einstein notation, the only thing that we need to understand is that repeated indices imply summation. So suppose, this is very important, okay? Repeated indices imply summation over those indices. If we look at this expression, for example, we have A sub I, B sub J, C sub J, okay, J is repeated, D sub I, so I is also repeated. So we can say that I and J are repeated indices. And we also have J sub K, H sub L. Those are not repeated, so K and L are free indices. Okay? So remember, repeated indices imply summation. So we have I and J as repeated indices, and this implies that they have a summation. So we can write these as this summation here. So for example, J would vary from 1 to 3. Why 3? Because we are working the three-dimensional space, as I told you before. But it could be any dimension. And if it was dimension 6, for example, I would have to substitute the 3 by 6, right? Because here I am explicitly saying the dimension that I want, 3 or 6 or whatever. But here I'm not saying, I'm not specifying the dimension. And that is one of the things that makes Einstein notation so neat, so compact. We don't have to it works for any dimension, not just for 3 dimensions. And besides, we don't have to write this summation, which is a big symbol here. So the notation becomes very compact. When you also have a summation over I, which also varies from 1 to 3. So, and we have those free indices K and L, and this will result in a component that depends on the indices K and L. So we can represent this as W, K, and L. And this summation here will be just a scalar, because we know those coefficients. If J sub K and H sub L do not depend on I and J, we can take them out of the summation and rearrange these equations like this. We can separate those summations into the I summation and J summation. We can expand these terms like this, and then we can perform the distributive multiplication between these terms. I'm not gonna do it. You can do it if you want, but you see that these terms are known, are numbers, so I can perform the multiplication. So look at how compact this notation is. If we did not use this notation, we should use this one or this one. They're all big examples, and they can get very, very big. I'm gonna show you the examples why the Einstein notation is very important. So if we consider rank 1 tensor, for example this vector v, we can represent this vector like this, or we can use Einstein notation, and using Einstein notation, this vector v can be written just like this: vi e hat I. Remember, repeated indices imply summation. So the I here is a repeated index, so this implies that there is a summation symbol here over I, and I goes from 1 to 3. Okay, so we just don't write this because it's implied. Whenever we have repeated indices, it's implied a summation. This is very important again. For a rank 2 tensor, we can represent it like this. For each pair of directions, we have a number, we have a coefficient with two indices, and this can be represented using Einstein notation like this. So we have A sub ij in the direction E hat I, E hat j. So you see that I is a repeated index, j is also a repeated index. So this implies a summation over I from 1 to 3 and a summation of j from 1 to 3. So this big expression here can be represented by this simple notation. For rank 4 tensor, it becomes even crazier, because then we have 81 components. We would have to write 81 components. It's completely impractical to use this type of notation. But if we use Einstein notation, we can just represent this tensor like this one. So we have I sub ijkl in the directions E hat I, E hat j, E hat k, E hat l. This is a very, very compact notation. We also have the Nabla operator. The Nabla operator can also be represented by Einstein notation. So the Nabla operator is given by like this. Using Einstein notation, we can write it like this. So we can see that the partial derivative with respect to x1 in the direction E hat 1, 2, 2, 3, 3, I. Okay, so this would be the partial derivative with respect to xi in the direction E hat I. The reason I'm using del sub I instead of del over del x sub I is to fit in one single line. I could have written here del over del x sub I in the direction E hat I. Okay, but that would take two lines. So if I write this, it just fits in one line. It makes even more compact. So whenever you see this del I, please understand del over del x sub I. Okay, so this is the Nabla operator using Einstein notation, and we are going to use this a lot throughout this presentation and in part B of this presentation. Okay, so these are some important takeaways from the presentation of today. The internal product for the basis vectors. So the internal product between E hat I and E hat j is the Kronecker delta function. The Kronecker delta function of I and j will be 1 if I equals j, and will be 0 if I is different than j. We also defined the Nabla operator that can be represented like this. This is a vector. The Nabla operator is a vector. And using Einstein notation, we can write it like this. Del sub I, E hat sub I. The Einstein notation, the only thing that you have to keep in mind, or at least the main thing that you have to keep in mind, is that repeated indices imply summation. If the index is not repeated, then it's a free index. When we also saw the concept of tensor, we saw rank 0 tensor. Rank 0 tensor is a scalar. Rank 1 tensor is what we call a vector. Rank 2 tensor, we often call it just a tensor. But we can have rank 3 tensor, rank 4 tensor, rank 10 tensor. Rank 10 tensor, each component will be associated to 10 different directions. Okay, so this is what I had to present today. Thanks for staying with us until now, and thanks for watching.